Hello and welcome to this presentation by me, John Hayward, entitled Exploring System Behaviour Using Model Structure. And this is part of the introduction to the loop impact method given at the International Conference of the System Dynamics Society in 2020. When we're looking to explain behaviour in system dynamics models using structure, what do we mean by behaviour? What do we mean by structure? So I'm going to put 4 questions before you. What behaviour do we seek to explain? What structures do we use to explain it? And how do we measure the effect of a structure? And then finally, once we have those measures, how do we decide which structure is dominant? So I'd like to consider those 4 questions in the light of a specific example. For that example, I'm going to look to the limits to growth model, and I want to picture a scenario of a business park where a fixed amount of land is designated for a new trading estate in order to encourage businesses to move into that town. Initially, the trading estate will grow rapidly as there are more businesses, attract more business developments, and that's called the urban attractive hypothesis. However, as growth continues, land availability falls and business construction is reduced. Now let's capture that. Let's use a stock to measure the number of business structures, and that stock is controlled by a flow called business construction, and this measures the number of businesses being constructed in a given period of time. Now, the urban attractiveness principle is the more business structures you have, the more businesses want to move to the park. And so this corresponds to a link between business construction and business structures, and that closes the feedback loop, R0. This is a reinforcing loop. The more business structures, the more business construction, so the more businesses are added to business structures. But the business park is limited in area, and so business construction will always also be limited by the fraction of land that is available. And if that fraction is smaller, it's going to be harder for new businesses to move into the area. The fraction of land available depends on the fraction occupied. The greater the fraction occupied, the less land is available. Now, to work out the fraction occupied, we need the land area. We need how much land each business structure occupies. We assume each one occupies the same amount. And of course, it depends on the number of business structures. And this gives our second feedback loop, B1. The more business structures, the more the land is occupied by businesses, the less land is available, and so business construction slows. And there's the 2 feedback loops of a limits to growth model. One reinforcing loop, one balancing loop. Both are first order because they only go through one stock. The solution is well known. It's the classic limits to growth S-shaped behaviour. There's an accelerating phase and there's a decelerating phase as it reaches its limit. And most people realise that the reinforcing loop has got something to do with the accelerating phase, and that the balancing loop, B1, has got something to do with the decelerating phase. What we'll do in the loop impact is work out precisely where that cutoff takes place and where the effect of R0 on the behaviour gets smaller than the effect of B1 on the behaviour. Well, having looked at that behaviour of the limits to growth model, I would suggest that the behaviour that we seek to explain is the curvature of the stock behaviour. The first part, where it speeds up, which we'll refer to as a plus for acceleration, and the second part, where it slows down, which we'll refer to as a minus for deceleration. And my second question, what structures do we use to explain it? Then the natural structures that we have here are the feedback loops R and B, or more specifically R0 and B1 that they were in that particular model. We'll defer the other 2 questions until later. So let's have a look at our structure. Two first order loops. R0 affects business construction, the flow, and B1 affects business construction. And they both affect it all of the time. It's just that some of the time R0 has more effect, and at other parts of the time B1 has more effect. And what we're claiming is that the accelerating phase is due to R0, and we're going to label that with a plus. That's where the stock behaviour changes in stock behaviour, it's speeding up. And after a cut-off point, it is the loop B1 which is dominant, explaining the slowing down behaviour, and we'll refer to that as a minus, and that comes from the first order loops. So we've got plus for speeding up, minus for slowing down. So plus for accelerate, minus in this case for decelerate. And that's come from the first order loops. So, first two questions, quite straightforward for this example. Let's move on to the third question. How do we measure this effect? Now, this is the key bit of the loop impact method. The loop impact method is a method for measuring the effect of a loop on stock behaviour. In particular, it measures how the loop affects the curvature in stock behaviour. So how can we identify a loop with curvature? Let's look at something a bit more complex, with acceleration and deceleration, and with an increase in stock value and a drop in stock value. The plus is labelling the acceleration in this first phase here. After the inflection point, it starts slowing down. This is the minus, this is the deceleration. It reaches a maximum. At that maximum, the stock value is now going down. But it's accelerating, so it's accelerating downwards, so I'm going to call this a plus. And then there's another inflection point, and at this and after there, the slowing down, it's slowing down again. Although it's decreasing, it's not decreasing as much as it had been in the previous phase. So we'll say that's a decelerating phase, bringing it to a momentary stability. Acceleration, deceleration, acceleration, deceleration. Now, you can't get behaviour like this unless you've got at least two stocks, and you've got at least one loop that goes through both those stocks, and that's what I mean by a higher order loop. This is not behaviour you can get in a single stock model if everything is explained endogenously. So in fact, I got that from this particular model here. Two stocks A and B with a balancing loop running between those two stocks, and that is a second order effect. If you look at the two stock behaviours A and B, and you'll see that A is increasing but is decelerating. Then after that point, A is then decreasing, but it's now accelerating until it hits the axis and stops. B, on the other hand, is accelerating, but it's going downwards, and it's decreasing all the time. It gets to its inflection point, and although it keeps going down, it is now decelerating until there's no A left to influence it, and everything stabilizes. And if you wonder why it stops, notice all these flows are uniflows, so they can't change direction. A and B do not take negative values, and there is an outflow from A with no feedback associated with it, and that is why this crashes in behaviour. What's interesting is that the accelerating phase of the one stock is the decelerating phase of the other stock, and when the one flips, the other flips, and they have to match up to preserve the fact that this balancing loop is always this balancing loop, second order balancing loop, is always balancing. If one is accelerating, the other one needs to be decelerating to keep that balancing polarity. So we're going to associate signs with this. Second order balancing loop has different effects on the two stocks at different times, but the product of their signs is always negative because it's a balancing loop. So this was accelerating, we call it plus. This was decelerating, we call it minus. This is decelerating, so we put a minus. This is accelerating, even though it's going downwards, and that's a plus. And notice the plus and minus always multiply to give a negative effect, and that is the polarity of the second order balancing loop. So first order loops are quite straightforward, but second order loops can indicate a change of behaviour during the course of as time progresses in the model. In fact, oscillation is explained by one single balancing loop, where at one time one is accelerating, the other one is decelerating, and they keep swapping round, and that is the standard oscillating model. So how do we measure the effects of a structure? We measure the effects of the loop. How can we measure the effects of the loop on each of its stocks? So it's actually important that when we talk about the effect of a reinforcing loop, we talk about the effect on each stock, because its effect on one stock is going to be different to the effect on another stock. So all we've done at this minute in time with question 3 is generate another question. How can we measure the effects of the loop on each of its stocks? And that leads us to the definition of loop impact. And I want to arrange it so that the impact of a loop picks up the plus for acceleration in this growing phase and this declining phase, and that the minus for deceleration is picked up in this growing phase and in this declining and decelerating phase. So how can we do that? Well, let's look at the rate of change. The rate of change is positive if the graph is increasing, and it's negative if the graph is decreasing. So in these two regions the rate of change is positive, and in these two regions the rate of change is negative. And the rate of change is sometimes called the first derivative in calculus. It also refers to the slope of the graph, and in mechanics it would be called the velocity. Acceleration is a little bit trickier. This is the green symbols. This is clearly accelerating by any understanding of the meaning of the word accelerating. But what's happening from this point on is there's a deceleration that brings it to a halt and brings it back. In other words, there is a negative force pulling something back, if we think of the mechanics analogy. And then there would be a positive force slowing it down. Now, these were not the signs that we had reproduced. If you remember anything from calculus on maxima and minima, you will know that the second derivative is negative either side of a maximum point, and it's positive either side of a minimum point. So the mathematical second derivative is not really telling us what we mean in system dynamics by acceleration, which is a plus link, and deceleration, which is the negative link. So what we do is we divide the two. Impact, which will pick up the impact of the loop and get the polarity correct, takes the acceleration and divides it by the rate of change. So in this region, we got the green plus divided by the red plus, giving me the plus that I require. In the second region, the green negative is divided by the red plus, giving me a minus. But in this region, where we know this is now an accelerating curve, the minus from the mathematical acceleration is divided by the minus for the decrease in stock, and that reproduces my positive sign for a positive impact and accelerator. And then at this point we've got the deceleration behaviour. So essentially the signs are flipped. when you've got a declining stock curve. So let us have a look at how we can apply this idea of the impact of a loop to the limits to growth model that we had earlier. And the impact of a stock on a stock is always via a flow. And so business structures has an impact on itself via R0, and it has an impact on itself via B1. And impact is this ratio measure, the acceleration divided by the rate of change. So the ratio in this case is the change in the flow that's been induced by R0 divided by the rate of change of the stock. And for B1, it is the change in the flow induced by B1 along this pathway divided by the change in the stock. And we can see at the beginning, if we plot out these ratios, R0 is by far the largest, B1 is almost 0 because there's plenty of space. And as the number of business structures increases, the impact of the loop R0 is getting smaller, whereas the impact of the loop B1 is getting larger. Now, of course, R0 has got a positive impact, so that's why it's above the 0 line. B1 has a negative impact, and that is why it is below the 0 line. At this point, they are numerically equal, and that is the point of transition between the loop R0 and the loop B1, as measured by this concept of loop impact. And it carries on that way. R0 eventually becomes 0, the impact of R0, and the impact of B1 eventually stabilizes out. And in a system as simple as this, you can do the mathematics and actually derive formally for the impact of R0 and for the impact of B1. So if we just take the absolute values of those two impacts, we can compare them on the graph, and you can see that R0 is numerically bigger here, and B1 is numerically bigger after this point, and that is the inflection point, which would be familiar to people who do calculus. So let us go back to this second order model that we had and look at a slightly more complex situation in determining the loop impacts. Now, we don't have to worry about loop dominance in this case. This second order model has only got one loop, which I've called B1, so it obviously dominates throughout. One thing we can do with that loop is we can work out the loop gains. So I've put some numbers on the two converters that govern the flows, and called 1.3, 1.2, and the loop gain is just the product of the two in this case. The minus sign reflects the fact that the outflow from B is minus, and that gives us the expected negative loop gain for a second order loop. There's no loop on outflow at A, so there is it is a one loop model, even though this flow clearly does affect behavior. It doesn't affect the acceleration or the deceleration in the behavior. So let's compare our time graphs of A and B, which is the top graph, with the loop impacts worked out according to our ratio measure of the acceleration divided by the rate of change. Probably easier to look at stock B first. It's declining throughout. It's accelerating in its decline to this point, and it's decelerating afterwards. Now here's the loop impact. It's dropping in value. It's positive. It's above the 0 axis. It becomes 0 at the inflection point, and then it becomes negative, as we expect, for the decelerating phase. Of course, to match that, A has to be in the negative region. Its loop impact has to be in this negative region. And although it's growing, it's decelerating because it's slowing down. So that's reflected by the minus. But notice that the loop impact in this case is getting larger and larger numerically, and it's heading off to minus infinity. And the reason for that is that loop impact is a ratio measure. And at this point, on the maximum point, the rate of change is momentarily zero. So the impact of the loop on that stock, A, at that point is going to be momentarily infinite. Now that's just the measurement, you can't avoid that. And at that point it flips, and now it comes down from plus infinity. This is called an asymptote sometimes in mathematics, and you can see that the impact is now positive to match the negative impact of the on the B stock, and it eventually declines to zero. Don't worry what happens after it crashes and hits the axis. That's going to be spurious. So while one impact is zero, the other impact has tended to an infinite value. Now at any point, if I take the two impact values and multiply them together, I will reconstruct the loop gain. So at time equals 5, which is about here, I've worked out the impact of the loop on A is minus 0.679. The impact of the loop on B is 0.0883. Multiply that together and I reconstruct my loop gain that I obtained earlier, minus 0.006. And I could take that at any point where I could do the computation along that graph. The product of the loop impacts is equal to the loop gain. Now it's only with loops with two stocks or more are you going to get this behaviour where polarities flip. But if the polarity on one stock flips, the polarity on the other will flip. And if there's three stocks in the loop, then the three will have to flip in order to preserve the loop gain of that loop. So we have answered our third question. How do we measure the effect of a structure? Loop impact, which is a ratio measure of change, the ratio of acceleration to the rate of change. Finally, how do we decide which structure is dominant? Well, for this, I want to consider a hypothetical system dynamics model with 4 loops. 3 reinforcing loops, R1, R2 and R3, and 1 balancing loop, B1. And rather than work out the loop impact, I'm going to take the loop impact as a percentage of the whole, and 55% of the loop impact is on B1, and 30%, 10% and 5% on the 3 reinforcing loops. And not surprisingly, we can say that the balancing loop B1 is dominant, and this will have a balancing behaviour. We have a clear dominant loop. If, on the other hand, 55% of the loop impact were on R3, then this would have reinforcing behaviour, and clearly R3 is our dominant loop, and we haven't got to worry about the other loops. Things get a bit more complex if there's no single loop with more than 50%. So we've got the balancing loop B1 in this case with 40% of the loop impact. And although only 35% is in R3, R3 is clearly having less impact than B1, but adding R3 to R2 is giving us more than 40%, and that is the dominant, and that determines the behaviour. That's the dominance. So it's reinforcing behaviour. There is more reinforcing effect than there is a balancing effect. In other words, there are more forces of acceleration than there are forces of deceleration, if we take that mechanics analogy. So how do we decide what is dominant? Well, R3 is clearly the largest contributory loop, and that is one definition we can use. But that doesn't really explain why it's reinforcing. I need to go to the next one to say, well, actually, it takes a dominant loop set to determine the reinforcing behaviour. So that's our definition of a dominant loop set, the minimum number I need of loops I need to add together to explain the behaviour that I see. Of course, you won't always get a unique answer to that. Clearly, in this case, with only 35% of the behaviour in B1, this is going to have reinforcing behaviour. The R2 and R3 can clearly be a dominant loop set because their sum total beats the 35 of B1, but I could have added R2 to R1, which also is higher than the loop B1. Somehow that doesn't seem as convincing as having R2 and R3. So the definition of dominant loop set that I normally will work with will be the minimum number of loops that are the largest that I could take to explain the behaviour. But it is clear there can't be a single answer sometimes to the question which loop is dominating at this particular point in the trajectory of a particular stock. So sometimes you may need to give a more nuanced answer than just say a dominant loop set. So our questions have been answered. What behaviour do we seek to explain? Stocks, in particular the curvature in stock behaviour, whether they speed up, plus, or slow down, minus. What structures do we use to explain it? Feedback loops, either reinforcing ones or balancing ones. How do we measure the effect of a structure? We use loop impact, which is the ratio measure of change. How do we decide which structure is dominant? We normally will use the dominant loop set, but alternatively we might take the largest contributory loop. Now if you move on to IC Exchange, and on IC Exchange you can do a search for loop impact, and we can look at the limits to growth archetype and play around with it, and look at a few other models as well to see how this concept of loop impact will play out, and that will be the next section of this presentation. So I've now moved on to the IC Exchange website, and to find the models I have there which deal with the introduction to the loop impact method, we can just type loop impact in the search engine, and all the examples, which are like tutorial examples for these introductory lesson in loop impact, are all here that you can try out. And I'll go through one of them just to talk you through how these online models work. You can, if you've got Stella, you can download them. I think these were done in Stella 1.8. I think this one's done in Stella 2, but it's they should work okay if you've got a reasonably up-to-date version of Stella. But of course they can be run online. So let's do this with a loop impact. You have a welcome page, which is the home page. You'll have a button that will set the scene, and this is what I read out about the business structures model earlier on in this presentation. You can view the model, and you'll notice in this case I've added in an extra balancing loop with an outflow for businesses that get demolished. We will come to that. And the all-important simulate page where we have our graph and the model will be there in front of us. References, help, contact of course, and one that you can do in your own time will be the explore model, where by following this through you can go through that model construction that I was showing you earlier. So let's go to the simulate, and there'll be instructions here, some explanation of the graph. On the graph on page 1 will be business structures, and I've got the actual values of the loop impacts on page 3 and the magnitudes of the loop impacts on page 2. The pages are adjusted here. an explanation for the loops, a bit of explanation about loop dominance, an explanation for the base run, and various suggested experiments. Now, you can do those in your own time, but all I want to do for this exercise is do a basic run, one where there is no business demolition, and it's just the two loops, which is the one we've already seen, and one where I put the business demolition in. So let's run. And I've marked on here the graph of the stock, which is S-shaped. The dashed line, axis running down the right hand side, tells me which loop is dominant. 1 is R0, 2 is B1, 3 is B0, and 4 is the combination of B1 and B0, because it could potentially be two balancing loops opposing the reinforcing loop. And in this case, this is the scenario we've already seen, and that's the transition point between R0. You see the 1 on the right-hand legend, and it changes to the 2. That's the graph we showed you earlier of the absolute values of the impacts plotted next to each other, and that's the point they're equal. And this is where the actual values, the one reinforcing loop's got a positive impact, the balancing loop has a negative impact. Let's introduce a small amount of business demolition. I don't know whether this is the value in the experiment, but it seems like a good run. Now what happens? There's now 3 loops. In this phase, R1 is dominating. That's the 1 down here. In this phase, B1 is dominating. That's the 2. But there's a central phase where it takes both balancing loops. That's indicated by the 4 on the dashed line legend, and that's B1 and B0. So it takes all 2 balancing loops to dominate over the reinforcing loop. That's the point of inflection. It's decelerating from this point onwards, but only from this point can you explain it solely by the loop B1. Of course, this period is so small, you might not think it worth including what the effect of B0 is in the explanation, although of course it has a significant effect in that it lowers the actual carrying capacity. If we increase that demolition rate, then there comes a point where it takes both loops to dominate for a considerable period of time. Let's pull that one slider back a bit. Yep, and now we have quite a wide range where it takes both loops to dominate before B1 takes over. Let's put all 3 next to each other. This is the point, this is the in-between region where 2 balancing loops are needed to dominate over the single reinforcing loop. And you can see at this point, if you added the green and red lines together, they would beat the blue line at that point. Let's actually look at the real values, and you can see that the B0, its impact is constant right throughout. That's just a little blip there after the numerical approximation. And for the early part, B1 has got less impact than the demolition B0. Now this is not impact on the growth rate, this is impact on the acceleration and deceleration. At this point they become similar, and from this point onwards the capacity loop B1 is having more impact than the demolition loop B0. But you can see even at the end, even though B1 is the dominant loop, B0 has still got a significant impact, and it's that significant impact that lowers the carrying capacity. So just because B0 doesn't appear in an explanation of loop dominance doesn't mean it's not having a significant impact on the stock behaviour. All loops are having impact. Even at this point, R0 is still having an impact. It hasn't disappeared entirely at that point. Let's try a different one. Let's take that one away. Let's try the inventory workforce model. I'll go straight to the simulate. You can spend your time exploring this, but this is a two-stock model, and there's a demand coming through into the sales rate, and the sales rate and the inventory shortfall are both being used to work out the number of staff in the workforce in order to get the correct production rate to meet demand. And this is a standard model. You'll find it in Sterman's book. And I've put it in equilibrium, so there is no loop dominance. There's a zero here. Nothing is happening. There's nothing to dominate the behavior of inventory. We put workforce on the other side. But I'm going to switch in a change in demand at a particular point in the time run. So let's run that. And as we can see, it oscillates. It puts it out of equilibrium, but equilibrium is quickly restored. At this point on the inventory, the dominance is indicated by 2, so the demand is dominating. Now, demand is not part of a loop, but it still has an impact, and its impact is bigger than the loop B2, which is meant to control inventory and bring it back to equilibrium. So B2 is this loop running through inventory control and running through higher rate back to production rate into inventory. Demand, of course, impacts inventory because it is subtracting material out of inventory. And at this point, the loop B2 kicks in, and it controls the oscillations and brings it to stability. Now, there's an extra loop involved with workforce, and this is a bit more complex. So initially, it is B2 that dominates the accelerating phase. So in other words, it's the requirements of the inventory that is determining the workforce. At this point, it's number 4. It's a combination. 4 is B2 and demand. So both demand and the inventory are now determining the workforce. That is the curvature in the workforce stock. How does demand influence workforce? Well, it comes to production required. It comes to the total production, the target workforce, staff needed, the higher fire rate, and into the workforce stock. That is not part of a loop. It is exogenous, but nevertheless demand does have an impact. Now at this point the loop B1 starts to kick in, and this is the first order balancing loop, and that's and that is slowing things down and attempting to bring stability. Of course, it's the second order loop B2 that turns the graph around and starts bringing decline again. But this loop B1 is absolutely critical, because this is like a resistive force, and with no resistive force you will not get equilibrium. B2 attempts to do control, but it doesn't dissipate any of that force that is coming in. So B1, as this rather innocuous looking loop, is absolutely critical to bring in stability to this system. So B2 dominates throughout there. Then eventually it's B1 that dominates again, and they jump back and forth between the two. This is typical of oscillations. Looking at things from a loop impact point of view, you would have the same with the pathway participation method as well, but not with eigenvalue elasticity or with loops that matter. They have a different way of looking at oscillations. And eventually I put a cutoff in because the oscillations are so slight they're not worth considering. It is interesting to note that what dominates on workforce is not what dominates on inventory. There is not one unique measure that captures the system when you look at things from this point of view, because we're essentially looking at forces on one stock and forces on another stock. Well, I think I can leave you to examine the other models. Limits to growth you've seen, look at it in detail. Gone with the Wind is a single oscillation, undamped, and that will give you an insight into how oscillations work. Inventory workforce you've just seen, there's much to explore there. Overshoot and collapse, well-known system dynamics archetype, as is the spread of disease. And urban business dynamics is an expanded version of limits to growth, which, if you have time, is worth an investigation. So thank you for listening to this presentation, and any questions, please go to the Sociomechanics website, and there you will sociomechanics.com, and there you'll find there's a contact page where you can get in contact with me. Thank you.